Go, go, go.
All right, let's talk about test 3. Get the light out of my eyes. Menu, iris, manual, menu, close, 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 close. All right. So this semester, test 1, well, let me get the bigger one. Test 1 has been 15%, and that's kind of an introduction to taking physics tests. Test 2 bumps up to 20%. Test 3, now we're getting into some real situations. And then the final is 30%. To put some things into perspective, the homework is only 10% of your total grade as something to like just ponder and meditate upon. The multiple choice of test 3 is worth more than your entire homework grade. So it's really something to think about. Primarily the homework is just so you can get stuff done. I have to make it worth something, otherwise I'd make it worth nothing, but then none of you would actually do anything. So really the tests are where your grade is decided, and I want you to spend most of your effort. All the tests have the same format, 25 multiple choice, 2 points each or 50, 1 appetizer, 5 points, total of 5, and then 3 problems at 15 points, 45, total is 100. And so that has been consistent throughout the semester. Do they want to come in?
Probably not, but...
Oh. Okay. Next, really what we're here to do today is talk about the layout of the test. Location here, obviously. Not in the JAC. When Thursday 4 to 5:15. In terms of the layout of the test, or in terms of the timing of the test, I've been very happy with still continuing to say that an average student will get done in an hour. There are always those just insane people who get done in 30 minutes. For the most part, the trickling comes in at about 50 minutes. It's a steady stream in an hour, and then those are and then the ones in an hour 15, I gotta pry it out of their cold dead hands, and that happens every single time. But so far the layout of the tests have been okay. In the morning, we covered a series of tests that came from June of 2015. And so in this test, we went over, hold on. In this test, we went over the general layout. Couple things to note. I'll be purging these letters called row sub L. These are the same things as lambda. The other part is we didn't cover ideal gas law, so anything mentioning bubbles changing volumes and stuff like that will be removed. Doppler shift equations will be placed in. And this morning we went through a lot of the multiple, or pretty much a lot of the multiple choice of one of the tests, and we'll be going over stuff like this on your version. But that video of this lecture, this morning's lecture, is already on YouTube, and this one will be up shortly. The one thing that I did want to point out, the appetizer from this test is not appropriate for what we've been studying, so it can be completely ignored. Now, what the test is going to cover, before we get into our copy of the test, the general layout. Appetizer will be oscillations. Either spring or simple. If you get a spring tomorrow, then you know simple is going to be on the final, or vice versa. And then there are three, like sound, Doppler shift, fluids, and then the Atwood string. The sound in the Doppler shift, you could have something and it's Doppler shifting, it's moving, and you need to figure out why. It could be a straight up Doppler shift. It could be a roulette wheel Doppler shift. As a reference, the roulette wheel, in fact, I think we're going to do it again today. The roulette wheel example covered today, the tutorial on Friday, and then your lecture last Thursday. So there were 3 times where I did this, and well, 2 times that I have done this, and 1 more time that we're going to do it. As for specifics, well, we'll pretty much take a look at stuff like this right now. Let's take a look at the multiple choice. Standard contract for a test. Read everything, assume I'm not a psychic, no notes, no books, all that fun stuff. The equations are listed. Yes, Bernoulli's equation is listed. I'm going around and figuring out if I need any more. But the stuff like, I'm trying to think if there are any equations. I think all of these are relevant. But now what I've done is I've gone through and I've marked all the correct answers. And we're not going to go through them right now. But what I have done is on Blackboard, the 3 versions from last summer and the 3 versions from the summer before are in 1 mega file. And it's like MC Sol. And so you can just download that and take a look at all the different versions. A lot of the multiple choice are getting little tweaks. I'm just proofing and improving things. This is something that I had to point out to the morning class because they didn't get this. It was a new change. What I had done is I had drawn on the last page of the multiple choice a series of curves, and there were a whole bunch of questions such as, and we can go over this right now, all of these are strings which are fixed at both ends. So which one of these has 2 nodes? 1. Second harmonic is what? 2, yes. Which is the 0th overtone? Answer, that's a dumb word. Fundamental frequency is what? 1. Another word for fundamental frequency is what? First harmonic. How many antinodes in number 4? 4. How many nodes are in number 4? 5. What's the relationship between nodes and antinodes? Yeah, there's always one more node than there is an antinode. And so you get stuff like that. Which parts move the most? Nodes or antinodes? Antinodes. And so stuff like that. And so there'll be like 4 or 5 questions like this. And so you can look through the tests and find them. But when I say, string 4 is that one labeled as 4. And so they'll either go, I haven't figured out where I'm going to put them. They're either going to go at the end of the multiple choice or on your equation sheet. One of those 2 locations. They'll be somewhere. One of the things that I am trying to do is the students were they were a little bit confused, and I don't like way confused students, is stuff like this. You measure period of a simple pendulum, it's 3 seconds. You increase the mass at the end of the pendulum, its new period can be 3 seconds is the answer. But these weird sum of the torques is equal to 1 joule, the nonsensical stuff I'm going to try to get out of the system. So stuff like this, where E final is E initial, that'll get chucked. So let's look at the problems. All right. So looking at this, let me see what. Oh, okay. All right. I will say this. I'm taking great pride in the fact that the numbers work out nicely. Like 4. You're not going to get an answer of 4.892762128252 blah blah blah. It'll be 4. So if you don't get an answer that's a whole number, you know that you've messed up. Also, there will be problems where you see stuff like given a simple pendulum, and what's really interesting is that the faculty meeting is right before this class, and one of the things that we're talking about is that students don't know how to problem solve, and that's been one of the things that I've been trying to just pound away. When you do problems, this is how I typically do them. Given a simple pendulum, stop. What do I know about a simple pendulum? I know that it's T equals 2 pi square root L over G. Like I start doing trench warfare, just go word by word by word. It's a simple pendulum, it's gotta have gravity, doesn't care about mass, that kind of stuff. It oscillates 4 times. Stop. That means N is 4. In 4 pi seconds on Earth, that means T is equal to 4 pi. Now, what does it mean when you see a weird time that isn't like 4 seconds or 5 seconds? It's actually 4 times pi seconds. That means I was trying to play the numbers so that everything worked out right. So you see 4 pi, that means Dr. Eschenburg's got your back. He's actually working through the numbers and making sure they work out nice. Earth, gravity is 10. What is its length? So I'm looking for length. One of the things, I'd be free to give you this, but it's pretty obvious. Total time is n times period. So if a period is 5 seconds and it oscillates 5 times, the total time is 25 seconds. Or you could say period is total time divided by n. So total time divided by n is 2 pi L over G. Now I'm extracting L. T squared, n squared, 4 pi squared, L over G, T squared, G over 4 pi squared, n squared is equal to L. So this is 4 pi, 4 squared, pi squared. G is 10. There's 4 pi squared. N is 4. And then I square it. And now you see the wonders of cancellation. 4 squared, pi squared, 10 over 4. L is 2.5 meters. And so that is the appetizer. Just a straight, quick in, quick out. All right, number 2, or the problem 1. A helium-filled sphere is tied to the ground with the string. So we have that. I have a tension of 1,000 newtons. It is helium inside and it's air on the outside. That begs the question, did I give you guys the densities? Yes, I did. And a lot of times if you go, you didn't give us the density, I was like, and if my response is, it is a correctly constructed problem, that's me saying, read the equation sheet. So density of helium, 0.18 kilograms cubic meter. Density of air, 1.3 kilograms per cubic meter. Okay. I want to know the mass of the balloon. And basically what I'm looking for is I'm looking for the mass of the shell of the balloon. So the balloon has several forces. Has the buoyant force, which is the density of air, volume, and gravity. Volume, 700 cubic meters. I have the tension being pulled down. I have the mass of helium times gravity. And then I have the mass of the balloon times gravity. And so those are all the forces acting upon this balloon. Also, one thing that you're always going to need on a regular basis, the Swiss Army knife of equations. Rho is mass over volume. Rho V is equal to mass, and V is mass over rho, depending on what you need. Now we know that it's tied down, and so because it's tied down, it's in translational equilibrium. Sum of the forces in vertical is equal to 0, which is equal to buoyant force minus T minus mass of the balloon, gravity, minus mass of the helium, gravity. And those are all the four forces. I'm looking for the mass of mass of the balloon. I'll keep the G in there, one last line. Divide by G. Now I go and substitute stuff in. The buoyant force, density of air, volume, gravity over gravity, minus tension over gravity, minus mass of the helium. Well, I don't have the mass of the helium, but I do have the density of helium times volume. Now to clean this up, density of air, volume, minus T over G, minus rho HeV. And that's the mass of the balloon. Mass of air, 1.3. Volume, 700. Minus 1,000 divided by 10. Minus rho helium, 0.18. Volume 700. And that gives me $684 kilograms. So that's the mass of the balloon. So it was just a straightforward sum of the forces in vertical. All right, next, the Atwood string. Given the Atwood string shown, determine the missing value that is listed in the box. Mass of the entire string needs to be determined. The hanging mass is 1,600 kilograms. L1 is 1.5. L2 is 4. Frequency 400 hertz at second overtone. Second overtone means what N am I going to use? 3. That's everything that I need. Okay. So the tension is the sum of the forces in Y. So the tension is just the hanging mass times gravity. Just getting that out of the way. The frequency is NV over 2 vibrating length. Is my vibrating length L1, L2, or L1 plus L2? L1. Now V in this case is the tension over linear mass density. So this becomes N over 2 L1 tension over lambda. Now tension is hanging mass times gravity. Lambda is the mass of the string and is its length L1, L2, or L1 plus L2? L1 plus L2, the total length of the string. So F is N over 2 L1, mass hanging gravity, L1 plus L2, mass of the string. Because, and people will like, well, why is it like this? 1 over lambda, which is how it's listed here, is L1 plus L2 over ms. So really, what you need to be able to do is derive this equation. Start from this, get to there. Do not have a miracle happens, poof, there's the equation. Because if that happens, the graders have been instructed to just get the biggest red marker they can find and just coat the entire page with blood. And we've brought in a special vial of leprechaun blood. It's very hard to get. So, that joke worked well better this morning for some reason. So, what we have is we got to solve for ms. Frequency squared, n squared over 4L1 squared. Hanging mass, G, L1 plus L2, ms. Solve for ms. Let's see, n squared over 4L1 squared, f squared, mhg, L1 plus L2. And that means we're done. 3 squared, 4L1, 1.5 squared, f squared, 400 squared, mh 1600, g10, L1 plus L2, 5.5. And that requires, oh goodness, 9 times 1600 times 10 times 5.5 divided by 4 times 1.5 squared times 400 squared. And I get 0.55 kilograms. Exact, no rounding. Which means if you see something like that, now I will say this in the problems, they're almost coming out as all whole numbers. If it is something like this, fraction to the nearest hundredth, that's still a good number. That's still an excellent number. So that's an Atwood's string. You should be able to derive, take this equation and solve for any of the letters. Well, L1 would be a little bit difficult, but L2 and everything else should be fine. Or at least what I would do, you could find L1 plus L2, and that's the total length of the string. All right, last problem, Doppler shifting. So we get that. I'm hearing mumbling, lots of mumbling. Number 3, Pied Piper passes you. You are standing still on a motorcycle. That means we got Doppler shifting going on. Is it a, oh, we could do this real quick. Before we do the problem, this thing just isn't focusing as well as it used to. All right, what we're showing is the next to the bottom line of the equations, all 4 equations from left to right, 1, 2, 3, and 4. Which 2 are the ones for the moving source? The middle 2. All right, this is how, let me label. I thought I was going to say. So 1, 2, 3, and 4 from left to right. Which ones are the moving source? 2 and 3. That means 1 and 4 are the moving what? Observer. If I'm a moving observer and I'm moving towards the source, which one do I use? 4. Am I going to hear a higher or a lower frequency? Higher. If we've got a moving source heading away, which one do I use? 2. 2 is going to produce frequencies that are higher or lower? Lower. That means 3 is a moving source towards. That's how easy it is. First thing I usually do with a test like this is I take those equations and then I just write down what they are, so I don't have to memorize or I try to figure it out on a later time. So it's a moving source coming at you and going away. Frequency that you hear as it's coming towards is 500. Thank you. Hertz. Going away. 200 hertz. I want to know speed of the motorcycle. Well, that's really the first thing that we got to do. That's actually away. What you do to get this, you take towards and divide it by away. Towards for a moving source, F over 1 minus V over Vs. For away, F over 1 plus V over Vs. The advantage of this is that we don't have to know what the frequency is. In a way, this is, I call it the roulette wheel solution, is a 2-equation, 2 unknown, where the two unknowns are the frequency of the source and the velocity of the source. This gives you 1 plus V over Vs. 1 minus V over Vs is equal to this. Cross multiply. Distribute. Now get the V's over on one side, non-V's on the other. Factor. Solve for V. Plug in towards 500 minus 200, 500 plus 200. So it's 300 times 350 divided by 700. And I get a velocity of 150 meters per second. So he is going fast, but he's not breaking speed of sound. Now the question that we have, the next question obviously that we need to figure out is what's the frequency? You can use either towards or away. We'll use away. Why? Because we flipped a coin. Frequency of away is F over 1 plus V over Vs. So Fa prime 1 plus V over Vs is equal to frequency. Frequency away 200, 1 plus 150 over 350, and that gives me the frequency. Number not so nice, but oh well. 285.7 hertz. And that's the frequency of the pipe. Now, what is the length of the Pied Piper's pipe? The pipe is opened on both ends and is at its fundamental frequency. Fundamental frequency, N is equal to 1. It's a pipe opened at both ends. Frequency is NV over 2L. Solving for L, NV over 2F. Now, N1. The V that we're looking for, this is the velocity of sound and air. When you were doing your lab this week, you're not using 0, which is the relative velocity of the pipe. No, you're using the velocity of sound and air, 350. And 2 times 285.7. And that gives you actually, it's a number that ended up being 0.6125 meters exact. And that's it. I would strongly recommend that you know the derivation for this. If you don't, if you just magically go, poof, there it is. They'll go, poof, there goes your grade. Just as that, you need to understand how to derive that. So there are a lot of things where I am hiding a few, I wouldn't say hiding. I mean, I can't just give you the test, but there are things that are just blatantly obvious. Roulette wheel solution, Atwood string. Why? Because until we all get it right, we're always gonna have Atwood string. There is a fluid problem. I'll tell them what, I'll tell the class this morning, or I'll tell you what I told them this morning. Problems like these are getting kind of stale. Those have been on the test quite a few times. So know your Bernoulli's equations, know your equations of continuity. If I was going to study for the test, I would definitely look at all problem set tutorials. I always get an email saying, why aren't there any solution sets? The videos are the solution sets. Basically, I work through all the solution sets, or all the problem sets on a video, so that's fine. I would look at, obviously, AM and PM lectures for today. The old multiple choice on Blackboard. And I'll tell you something that I didn't tell them from this morning. The test will not have the bucket of brains. So if you don't know what that means, just be thankful. Talk to a 213 student from last year and say bucket of brains, and then they'll just start shivering. Last year, There's no theme to the test. Last year, someone wanted a Walking Dead test, and I was like, challenge accepted. So that's it. We've still got a little bit of time. Do you have any other questions? Yes.
On the problem set, so we did interview number 11. Is there a chance of that popping up on the test?
You're talking about the one where it's, oh, this brings up some interesting points. There was a problem that looked like this on the problem set. And I told them not to do the very last one, which had the mass resting in the water. I don't require it for the problem set. It's not going to be on the test. Someone brought up the point. They were like, which one do you want us to know? This one or Atwood string? And I'm like, I have to apply the universal law that we will always have Atwood string, which means this is going to be on the test. That very likely could be on the final. So that's the big difference between the two. All right, motion on the floor to adjourn. I don't see anybody saying no. Going once, going twice. See ya.